Our baseline task is straightforward. Successfully classify a 28 by 28 grayscale image of a handwritten digit into a single, accurate output ranging from 0 to 9. That image contains exactly 784 individual pixels. In our input layer, those specific grayscale values map directly to the initial activations of 784 corresponding neurons. From there, the data filters through the hidden architecture. We rely on a somewhat arbitrary but highly functional structure here, 2 hidden layers containing 16 neurons each. To route the information through this structure, every single connection between these layers requires a specific weight to dictate the connection strength and a localized bias to determine when the neuron activates. The network contains roughly 13,000 adjustable variables. To understand how it learns, we drop the geometric visualization. The network collapses into a column vector. This abstraction shift is crucial. The 784 external pixels aren't the focus. These 13,000 internal numbers are the true inputs. At this level, machine learning is strictly the mathematical exercise of finding the optimal combination of these 13,000 specific variables. To begin that exercise, we initialize all 13,000 parameters entirely at random. This is our uncalibrated baseline. If you feed a real handwritten digit into this randomized state, the output layer generates arbitrary garbage. The neurons fire with low confidence and no recognizable logic. We need a programmatic metric to quantify exactly how incorrect this output is compared to the right answer. We calculate the mathematical cost of a single training example by comparing the generated output array to the desired target array. We find the differences, square them, and sum them together, merging into one massive number that represents the total error. A confused arbitrary network produces a severely high computational cost. A highly confident, correct classification drives that cost down to near zero. We scale this localized metric up to evaluate the entire system. By calculating the average error across tens of thousands of individual training examples, we define the macro cost function. This cost function is a secondary mathematical entity. It sits on top of the neural network, structurally distinct from the layers of neurons we built to process the images. It has its own precise parameters. It takes the 13,000 network weights and biases as its inputs and outputs a single scalar score, a measure of absolute lousiness. The training operation is a search for the absolute minimum value of this specific meta-function. Standard calculus allows us to explicitly solve for the minimum of symbol equations, but explicitly calculating the absolute minimum of a function with 13,000 independent variables is mathematically infeasible. This severe limitation requires a stepwise approximation. To understand how that works, we scale the problem down to a simplified 2-variable analogy. Plotting a 2-variable cost function as a 3D surface graph, the gradient at a specific coordinate gives the direction of steepest localized ascent, pointing straight uphill. We invert that arrow perfectly to find the negative gradient, charting the path of steepest downward descent. The vector dictates our next move. Its positive or negative sign acts as a binary instruction, telling us whether to nudge a parameter up or down. But look at the components of that downward vector. One axis stretches significantly further than the other. The relative magnitude of these components encodes the precise bang for your buck across the different variables. It tells us that at this exact coordinate, adjusting one specific weight will impact the total cost more significantly than tweaking a neighboring weight. Returning to the actual network, the 13,000 dimensional gradient is a prioritized roadmap. It ranks exactly which combination of parameter nudges will most efficiently reduce the overall error rate. This roadmap dictates the cyclical loop of backpropagation. Compute the negative gradient, take a localized step downhill, recompute the new slope at the new coordinates, and repeat. We mathematically tie the step size proportionally to the steepness of the gradient. As the valley floor flattens out, the algorithm takes progressively shorter steps. This proportional deceleration acts as the brakes. It mathematically prevents the algorithm from overshooting the minimum and endlessly bouncing up the opposite wall. But the topological reality of the parameter space complicates this. A 13,000-dimensional landscape contains a vast number of localized, highly distinct valleys. Because the terrain is so complex, the specific local minimum the network eventually settles into is heavily dependent on the completely random initialization coordinates from step 1. Once the descent stabilizes at a local minimum, we validate the parameters by locking them in place and testing the network against a dataset of entirely unseen handwritten images. This simple stepwise calculus allows the model to correctly classify 96% of the novel images it sees. Gradient descent reliably optimizes the parameters to classify the data, yet the exact nature of the specific minimum it finds heavily challenges basic human logic. We approach visual processing with a biological bias. Humans intuitively expect these hidden layers to build a geometric understanding of the data, progressing logically from simple edge detection to complex shape recognition. But when we actually visualize the parameters learned by the second-layer neurons, we find chaotic, unorganized, static-like pixel patterns. There are no clean lines or distinct loops. The optimization process carved out noisy artifacts that bear little resemblance to human perception. The math explains the disparity. The network simply found an arbitrary local minimum in an unimaginably large space, untethered from human geometrical heuristics. From the network's constrained point of view, the entire universe consists only of perfectly centered digits fixed inside a rigid 28 by 28 grid. This localized optimization creates a significant blind spot, which becomes obvious if we feed the trained network an image of pure random static. Rather than expressing uncertainty, the network outputs a high-confidence, entirely incorrect classification of the noise. Gradient descent creates an idiot savant. It generates a mathematical mapping that separates statistical features without possessing a generative understanding of reality. This behavior introduces a fundamental tension in modern research: true generalization versus brute force memorization. Modern networks suffer from severe overparameterization. They contain vastly more adjustable variables than are mathematically required for simple classification tasks. A paper presented at the International Conference on Machine Learning tested the absolute limits of this massive parameter space. The researchers took a highly structured dataset of images and completely randomized their corresponding labels. The expected outcome is an absolute failure to train. There is no underlying structural logic connecting a static image to a randomly assigned label. But the network achieved perfect training accuracy anyway. The massive parameter space was large enough to simply memorize the random noise through pure brute force mathematical adjustment. This creates a paradox. If a massive neural network can perfectly memorize random garbage, it raises the question of whether gradient descent learns underlying structure or just memorizes real datasets in the same way. The answer to the paradox lies not in the network's final output, but hidden inside the invisible topography of the optimization landscape itself. We can map this topography by comparing the training effort required for the two different datasets, plotting their respective loss over time. This graph maps computational loss against training steps. The line representing randomly labeled data charts a slow, shallow descent, but the trajectory for structured data looks different: a brief initial plateau, followed by a rapid drop plunging into a deep valley. The shallow curve reveals the shape of the mathematics. Random data creates a rugged, chaotic parameter space, where gradient descent struggles linearly to find any downward path. The rapid drop proves that structured data defines the topology of the multidimensional landscape, carving out massive, easily accessible minima. Gradient descent takes the path of least resistance. It is mathematically easier to fall into a structured minimum than to brute force a chaotic one. Deep learning functions because the underlying structure of reality configures the mathematics, guiding a blind calculus exercise toward reliable generalization.